In this video, we're going to talk about how to calculate the pH of weak acids and weak bases. First, what are weak acids and bases? We can get a good idea if we compare a weak acid to a strong acid of just what they are. Remember that if water is added to a strong acid, like HCl, then the hydrogen ion from the HCl is transferred to the water and we get H3O plus Cl minus. A similar thing happens when we combine hydrofluoric acid with water. We get H3O plus fluorine minus. The main difference is we'll draw a forwards-backwards arrow with the hydrofluoric acid. And what that indicates is that when we put a bunch of hydrofluoric acid molecules into the water, only some of them react with the water and split apart. Only some of them dissociate. So hydrochloric acid completely dissociates. That means if you put 1,000 HCl molecules into water, all of them will split apart. On the other hand, if you put 1,000 HF molecules into water, maybe only 1 or 2 of them will split apart. So what that's telling us basically, if we think in terms of our equilibrium constant language, is that this has a very large K. For strong acids, we get a K that's much, much bigger than 1. But for weak acids, we get very small Ks. So they don't dissociate very much, and that means they're reactant favored. Since we're dealing with acids, when we talk about equilibrium constants here, we add a little a next to the K. So we can look at the generic formula for that Ka, for the dissociation constant for acids in this way. First, remember that weak acids are those acids that only dissociate some of the time, so only some of them will dissociate, and they're considered weak electrolytes. So remember from Unit 2, we talked about what an electrolyte was. That's anything that when put into water allows it to conduct electricity. So weak acids and weak bases allow water to conduct electricity, but not very strongly, and so we call them weak electrolytes. Here we have the generic formula for the dissociation of an acid. We can just call any old acid HA, and when we mix it with water, we'll always get H3O plus and A minus. We can write the equilibrium constant, which is products over reactants, just like it was before, and we've dropped the water. So notice there's no water down here. We can do the same thing for a base. We can represent a base with just this B reacting with water. Notice that a base accepts a hydrogen ion. So here we have an extra hydrogen ion that came from the water, and it leaves behind OH minus. So because weak acids and bases only partially dissociate, we have to use different tools to calculate their pH. Basically, what we have to ask ourselves is, what is the equilibrium concentration of OH minus in the case of bases, or H3O plus in the case of acids? So that's going to be an equilibrium problem where we use an ice table. Let's do one of those. This one is for propionic acid. So it wants to know what is the pH of 0.5 molar propionic acid. And it gives us the Ka, the equilibrium constant. Well, the very first step here is we want to write the reaction of that acid with water. So I'm just going to copy down the acid, and I'm going to react it with water. That last hydrogen there is going to hop over to the water because acids donate their protons. I'm going to draw forwards backwards arrows because it's in equilibrium, and we'll get C2H5CO2 minus, it's minus now because it's lost a proton, plus H3O plus. So that's the reaction. And now we need to fill in the ice table. So I've generated here a nice ice table for us to fill in. And we're going to fill this in just like we did for our other equilibrium problems. We're going to put in the initial concentrations of our acid. That's 0.5. The initial concentration of A minus, that's this guy, that's our dissociated acid, that's the ion that's left over after the hydrogen ion leaves, is always going to be at 0. So our products we're going to consider to have 0 initially. And then our reactants drop in concentrations, so HA goes down. Remember, this guy is what represents HA. It's our acid with our hydrogen. A minus goes up, and H3O plus goes up. So at equilibrium, we get 0.5 minus X, X, and X. So we've written the reaction, we've filled in the ice table, and now we're going to write our expression for Ka. Remember that Ka is equal to products over reactants, and we don't include the water. So we're going to have A minus and H3O plus up top. And we're going to divide that by HA. So in other words, that's this guy and this guy up top, A minus and H3O plus, and this molecule on the bottom. Then we can plug in our equilibrium expression. So we have X times X up top, which we get from right here and right here, divided by 0.5 minus X. That's all equal to our Ka, which is 1.34 times 10 to the minus fifth. Here's a cool trick. Because our Ka is small, we can drop added or subtracted x's. So that means that guy can go away. And that's because when you have a very small number that you're subtracting, it doesn't make any difference. For example, say you have $1 million in your bank account, and someone comes along and takes away 0.03 pennies. It doesn't matter. You won't notice. Same thing here. I can't drop the other x's. The multiplied x's, those really matter, because if I multiply two small numbers, that gives me a really, really small number. So it certainly changes the number. But subtracting a small x, I can always drop. And so every single time that you have one of these weak acid or weak base problems, you can drop the added or subtracted x. So what that simplifies to is x squared over 0.5 equals 1.34 times 10 to the minus 5. So now if I want to solve for x, I multiply both sides by 0.5. That gets rid of that, and take the square root. Notice that because I dropped that x, I don't have to do the quadratic formula. And so that's really nice. It makes it much simpler. Taking the square root, you should get 2.6 times 10 raised to the minus third. Remember what we've just solved for. We've solved for the molarity of H3O plus. Further, remember that the pH of a solution is equal to the negative log of H3O plus. So the last step in this problem then is to take our calculated concentration of 2.6 times 10 to the negative 3 molar H3O plus and plug it into our pH expression. When we do that, we should get a pH of 2.58. So this is just like our other equilibrium problems, except for we can drop the added or subtracted x because of the size of our equilibrium constant. And then at the end, we have to use either our H3O plus concentration in the case of acids, or our OH minus concentrations in the case of bases to go to pH. Here we have ammonia, and we want to solve for the pH once again. It's going to look quite similar. Step 1, write the reaction. NH3 reacts with water. And because NH3 is a base, that means it's going to accept a proton. So a hydrogen ion is going to transfer back there, and we'll get NH4 plus OH minus. And now that we know the reaction, we can fill in our ice table. So that's step 1 and 2. So we want to fill in the ice table. Our initial concentration of our base, which we symbolize with B, is just 1.7. Of BH plus, that's our ammonia right there, is 0 initially, and of hydroxide, also 0. The base concentration is going to drop during this reaction, whereas the other two are going to increase. So our equilibrium expressions are 1.7 minus x, x, and x. Now that I've filled in the ice table, step 3 is to write my Kb. So Kb is equal to products, which is BH plus times OH minus, over reactants. Again, I drop the water because it's liquid from my equilibrium expression. All right, and then I plug in my equilibrium expression. So I get x and x up top and 1.7 minus x on the bottom, and that's all equal to the Kb of 1.8 times 10 to the minus 5. Once again, I get to drop the x because my K is small. Any weak acid and base problem, I can do that. That's going to give me x squared over 1.7 equals 1.8 times 10 to the minus 5. By multiplying both sides by 1.7, I get rid of that 1.7 on the left-hand side. Then I take the square root to solve for x. So that just leaves me with x equals that square root. When I plug that into a calculator, I'll do 1.8 times 10 to the minus 5 times 1.7. Take the square root. I will get 3.06 times 10 to the minus 5. Once again, ask yourself, what did we just solve for? That's our hydroxide concentration. So we've dropped the subtracted x. We've solved for x. Now we need to calculate pH. Here we have one extra step because hydroxide isn't directly related to pH. We have to first calculate pOH, which is equal to negative log of my hydroxide concentration. I do that by plugging this concentration in to my equation, and I'll get a pOH of 4.51. Giving ourselves more space to work with, we know that pH plus pOH equals 14. Since our pOH is 4.51, we can now calculate what that pH is. pH will be equal to 14 minus our 4.51, or 9.5. So that's our pH. So for weak bases, we just have one extra step of going between pOH and pH at the end.